Welcome to the Computer Science and Engineering Distinguished Lecturer Colloquia. Our speaker today is Professor Tom Mitchell from CMU, and I will just quickly review some of the highlights of his distinguished career. He's known as the father of machine learning, and now it's a hot field, but he started working on it in the 70s, and his dissertation work and the paper based on a generalization and search really served to define the field for many years and still even today. He won the Computers and Thought Award back in 1983, and in the late 80s he was a phenomenal advisor to me and been an inspiration ever since. In 1997 he literally wrote the book on machine learning called Machine Learning. He, about 5 years ago, created the machine learning department at CMU, and he still serves as the head of that department. He's been recently elected to the National Academies of Engineering and Science. And I would say he really typifies the passion and curiosity of a great researcher and combines that with a long-term vision that makes him one of the most influential researchers in machine learning and AI today. And I will predict that sometime in the next 10, 15 years, he'll win the Turing Award. Please welcome Tom.
Thanks. Well, it's great to be here, and I won't ask for a show of hands on who could not get into the Obama rally, but I'm glad you're here. So what I want to do is talk about a problem that I find very interesting, which has to do with a simple observation about machine learning and about human learning, which is simply that humans learn many things over their lifetime, and we become better learners over time, in fact, right? We learn first, for example, arithmetic, and then after we can add numbers, we learn algebra. And after we know algebra, we can learn calculus and on. And not just that, in parallel with that, we're learning how to ride bicycles and we're learning how to play tennis. But before that, we were learning how to just pick up stuff. And there's a whole lot of sequential and parallel learning tasks that we get better at over a long period of decades. And of course, computers don't do that. We have programs that we call machine learning programs. But in fact, most of them live a very short life. You give them a set of data, they crunch on it for a while, they give you the answer, and then they get turned off. And so the question is, why don't we get machines to do some more long-term, human-like, cumulative learning of many functions? So I think it's an interesting problem. It's kind of an underexplored problem for machine learning. When I say, let's do some work on never-ending learning, here's the kind of loose specification of what I have in mind. Why don't we start building systems that learn over years, multiple functions, where learning one thing makes it easier to learn the next thing. So there's some notion of staging and learning something that you're now able to proceed on that you weren't before. And of course, that'll involve a lot of interacting with the environment and humans and maybe other agents. And I think 2010 is actually a ripe time to be looking at these kind of problems. And you can look at them in a lot of different domains. I was talking with some people yesterday who I thought maybe should be working on robots learning. You know, there's a lot of robotics work here at UW. Why don't we have robots that roam around through the building for days and weeks and months and years and learn, initially, of course, they'd have to learn simple things like how to not collide with things and how to not run out of power. But after that, they might be able to learn more sophisticated things involving manipulation and retrieval and helping us with various tasks. So there are a lot of domains where you could do this. And in fact, there's a lot of work that we can build on. So one reason I think 2010 is a nice time to do this is machine learning and AI have covered a lot of the pieces of what you'd want to assemble into a long-term learning system. There's work on architectures for problem solving. There's work, in fact, on building large-scale knowledge bases, starting with some of Doug Lennett's early ideas of building a large knowledge base by hand, and quite a bit of work here at UW, in fact, by Oren's group and Dan's group and others on large-scale collection of knowledge from the web and other corpora. There's a little bit of work that goes under the name lifelong learning, which really doesn't quite live up to what we're after, but there are some ideas of how to organize systems that could learn one function and then use that learned function as a scaffolding for learning the next thing. A lot of recent work on transfer learning, namely learning a collection of different functions and then somehow coupling the training of those functions or using what you learned about spam filters for me to transfer when you try to learn a spam filter for you, and so forth. So there are a lot of pieces around, and so I think it's an interesting problem to consider. So what I want to talk about is a case study of this that we're trying to work on, which I'll call never-ending language learning, where the spec is just this simple specification. I want to have a system where I could input an ontology that defines categories and relations that I would like to learn to read. For example, I might be interested in categories like people and athletes and professors and organizations and universities and departments and beverages and emotions and other stuff like that, and relations among them, like which university offers which degree programs and so forth. But I input an ontology that defines the kind of things I'm interested in learning to read, and I'll give a handful of examples of each of those. If I'm interested in universities, I'll give a dozen university examples, University of Washington. The web, and occasional interaction with a person. And now the job is simply to build a system that runs, and every day it just has to do two things. It has to read more facts, extract more facts from that text to populate that ontology that I defined for it, and it has to learn to do that better than it could yesterday. And of course, the simple way to measure that would be if it went back to the same text that it looked at yesterday. If it's doing this, then today it should be able to get more facts more accurately out of the same text. Okay, so it's easy to write down a specification of what we would like. And in fact, I'm here to tell you we have not solved this problem. But we have been trying to make a start. And so what we have today is a system that was turned on in January of this year. So now it's about 10 months old. It's been running pretty much 24 hours a day since then. It has a set of about 500 categories and relations, like the ones we were just talking about. 10 to 20 seed examples of each. It's working on a downloaded collection of web pages, 500 million web pages that Jamie Callan collected. It also has access to a Google search API where it can make 100,000 queries a day in addition. And since January, it's been executing an algorithm which was intended to make it learn to read better each day and to do those two tasks we talked about. And so now it has a knowledge base that has over 400,000 extracted triples. And even though I mostly want to tell you about how the algorithm works, it's much more fun to show you what it has done so far. The system is on the web. You can browse this knowledge base yourself. You can download the entire knowledge base if you're interested, including the learned extraction rules that it has acquired over time. Here's a random sample of 10 recently extracted tuples or beliefs. So for example, it believes gazebo is a kind of furniture. Sale search is a musician. This is what happens when you take random samples, you know. Alex Barzouk is a male. Water sport imaginable is a sport. Gloria Delaney is a celebrity. WXII is a subpart of NBC. Jimmy is a musician who plays the guitar. That's right, go Seattle. Melbourne Museum is a museum in the city of Melbourne, which is harder than it sounds to get the Okay, you get the idea. I don't like that random sample, so I'm just going to pick another one. All right, but you get the idea. Cerebral angiogram is a medical procedure, right? All right, you get it. Apple Computer is a synonym for Apple Inc. Teachers is a profession that's a kind of practitioners, etc. So this is the kind of stuff that's in there. And, I don't know. We can pick any one of these and see what it really thinks. So Lincoln, it thinks, is a city that it believes to be the capital of Nebraska, located in Nebraska. I guess there isn't that much, never mind. How about Seattle? Okay, so it believes Seattle is a city. By the way, all this other stuff is why it believes Seattle is a city. So it believes Seattle is a city because it's found that it co-occurs in the context home loan resources for Seattle and promotional sales in Seattle and Major League Baseball team based in Seattle and so forth. Now, the reason it believes with very high confidence that Seattle is a city is not because it found a sentence that was very compelling. The reason it believes that Seattle is a city is that it's looking at 500 million web pages, and it's looking at every occurrence of Seattle in those 500 million web pages, and it's collecting a statistical profile of what the noun phrase Seattle co-occurs with. And it co-occurs, among other things, with these patterns. And it co-occurs with a lot of other patterns that it's not showing us. But these are the patterns that it has learned over the last 8 months are pretty good indicators of whether a noun phrase refers to a city. So no individual pattern here is perfect, but the fact that Seattle co-occurs with all of these, and inside it knows how frequently, and it has a weight associated with these different patterns, that's how it's making its decision that Seattle is a city. I am going to tell you how it works. So let's leave the browsing part of the talk. But you know, the talk is more motivated if you see what's in there. So there are about 400, there are over 400,000 of these kind of triples. You can browse this at your leisure, and that's what's in there. Okay, so now, and again, what we started with were the definitions of those kind of categories: city, television station, stadium, and relations, stadium located in city, and 10 to 20 seed examples of each. And then all those extraction methods were learned from that in what I think is a pretty interesting semi-supervised learning strategy. And I'll tell you up front that we spent about 3 years floundering and failing miserably to get the system to do anything interesting. And around summer of last year, it started being interesting. And I attribute that to 2 good ideas that are embedded in the algorithm. So I want to tell you about those 2 ideas and the algorithm. So to tell you the first idea, let's look at the most obvious way that you might do semi-supervised training. By semi-supervised training, all I mean is you're trying to learn some function, let's say, to classify noun phrases. That's largely what it's doing. Classifying noun phrases according to whether they refer to a city or not. That would be an example of a classification function you're trying to learn. And in supervised learning, you have some labeled examples. Here's a noun phrase, yes, that's a city. Here's another noun phrase, computer, no, that's not a city, etc. In semi-supervised learning, in NELL's semi-supervised learning, it has 10 to 20 of those labeled examples, and then it has billions of unlabeled examples. Actually, it considers roughly the 20 million most frequent noun phrases that it finds on the web. So it has roughly 20 million unlabeled noun phrases and, let's say, 15 labeled ones. Semi-supervised in the sense that it's trying to make use of this unlabeled data. So how would you do that? Here's the most obvious algorithm. If I give you 4 cities, and those are your labeled examples, then the obvious thing to do is to look through all that unlabeled data and find some contexts that co-occur with those cities, and then use those contexts to look for more noun phrases that must be cities. And, you know, live in San Francisco is great, live in denial is less great, but you will find these. And then you can use this augmented list of purported cities to find even more patterns and even more noun phrases. And this is the kind of thing that we and many other people tried. It doesn't work it works great on the first iteration, and then quite often it runs off the rails because a bad example gets in there like denial and pollutes the labeled data, and then things can easily run crazy. Now, you might say, what a terrible algorithm, but I don't think that's the case. I think it's a terrible problem formulation. You can't really fault the algorithm because we gave it an impossible task. If I say to you, here are 4 words, I have a magic, very complicated concept in my head, guess what it is? All right, not fair, right? Especially if I'm going to win $10 if you're wrong, then after you make your guess, I'll say, no, that's not it, right? It's completely underspecified. It's an under-constrained problem. And so to fix this, we should not look for a different algorithm to solve the same problem. We should look for a different problem that's easier to solve. And that's key idea number 1. Key idea number 1 in NELL is too darn difficult to learn a single function from a handful of labeled examples. It's an under-constrained problem specification. If you want to make an easier problem, force it to learn a lot of things. Sounds more complex, it is, but it's much, much easier because it's a much more constrained problem. In fact, instead of just asking it to decide whether a noun phrase should be labeled as a person, make it also learn whether it should be labeled as an athlete or a team, and make it learn relations among those, and somehow couple the training of all of those functions at once. And this makes the learning problem much easier. So let's drill down on that. So we could have a single function. So now what I want to do is we've actually identified 3 different types of coupling of functions that make learning easier, and NELL uses all 3. And here they are. The first one is this. Suppose this one goes under the name co-training or multi-view learning or co-regularization. There's some previous work on this, but the idea is kind of simple. If we have a function from x to y, and x can be described by 2 subsets of features, like let's say this is a noun phrase, x1 might be the characters that are inside that noun phrase. And x2 might be nothing about the noun phrase, just what are the contexts in which those noun phrases occur. And let's have it learn 2 different functions. One that just uses the letters in the noun phrase, the characters in the noun phrase, one of which uses the context around the noun phrase. And then we'll train it. Now, why does that help? That helps because, remember those many, many unlabeled examples? Every one of those unlabeled examples now suddenly becomes a constraint on the joint selection of parameters for F1 and F2. Why? Because if I give you an x1 and an x2 and there's no label, you can't tell me whether, let's say these are Boolean functions, yes or no, it's a city. You don't know whether F1 and F2 should say, yes, it's a city, or no, it's not a city. But you do know that if F1 says yes and F2 says no, something's wrong. And the parameters of at least one of those functions needs to change. So in that sense, every single unlabeled example becomes a constraint on the joint choice of parameters for F1 and F2. So that's one of the kinds of coupling that NELL does. In fact, instead of using 2 views, NELL uses 3. One of them is indeed the context around the noun phrase. It tries to classify based just on that. One is indeed the characters inside the noun phrase. It tries to classify just based on that. And the third one is what some people call wrappers on URLs, but essentially features of the form. If you go to this exact URL and you find this pattern, then the thing in the between there, that's the fact that it exists inside here is a feature. And by looking at these features, F3 tries to decide whether it's a city. Okay, so that's one kind of coupling, multi-view learning, co-training. And again, the point is, this makes each unlabeled example a joint constraint on the parameters for F1, F2, F3. Now we've got a more constrained problem. Okay, what's type 2? Well, type 1 says let's use different x's going to the same y. We could also use the same x going to different y's. For example, x might be a noun phrase, and F1 might be, is it a city? And F2 or Y2 might be, is it a fruit? And we might know a constraint between those two that nothing is both a fruit and a city, so they're mutually exclusive. And so now, just as before, for each unlabeled example, we don't know what Y1 and Y2 are, but we know that there are certain joint assignments that are impossible. They're outlawed by our constraint. If F1 says, yes, it's a city, F2 better say, no, it's not a fruit. And so again, there are now illegal joint assignments, and so every example, every unlabeled example gets converted into a constraint for us. And of course, in NELL, the obvious thing to do is have it learn these different classifiers. Classifier whether it's an athlete, whether it's a person, whether it's a coach. So NELL, in fact, learns all these Boolean classifiers of noun phrases, hundreds of them. And we tell it, as part of the ontology, what are the constraints that relate those different y values that it's trying to predict. The green ones, for example, means if you're an athlete, you must be a person. So there's an illegal joint assignment. You can't say yes to athlete and no to person. That's illegal. The red ones mean they're mutually exclusive. You can't be both a person and a sport. And these are simple constraints that kind of, well, that we input by hand as part of the ontology that we give NELL at the beginning. And of course, we can combine idea number 1 and idea number 2 and learn functions that predict many different properties of noun phrases from each of these 3 different views of the noun phrase. And now you start to see how by doing the cross product of these types of constraints, we get a bigger and bigger nest of interconstrained functions to learn. So there's a third kind of constraint, which has to do with learning relations and how that relates, how that couples to learning these categories. So NELL also, in the ontology, we give it relations to learn, like athlete plays for a team or athlete plays sport. And of course, if we, in the ontology definition, say for each relation, what are the types of the arguments, then that allows us to couple the relation training to the individual category training. So for example, we know that if the classifier that looks at a pair of noun phrases, NP1 and NP2, and says, yes, plays for team is true for Alex Rodriguez, New York Yankees. If it says yes, then it must be true also, then the athlete classifier must say that Alex Rodriguez is an athlete. Otherwise, we have an inconsistent assignment. So the relation type restrictions give us another form of coupling. So these are the three types of ways that NELL couples the training of what turns out to be over 1,000 different functions that it's simultaneously learning. And that's key idea number one. So how does it do that? I think of the NELL algorithm as an approximation, a crude approximation to EM. Those of you who know EM know that this would be, as a machine learning person, one of the first algorithms you would think of for doing coupled semi-supervised learning. What you would like to do if you had infinite computers and infinite time is you'd like to say with EM, you say, well, each of those black arrows is one of the functions that we're trying to learn, and it has some parameters we're adjusting, like maybe how much do we weight each of the contexts, or the different morphological features, or each of these functions has parameters that we're training. In EM, what we do is we use the labeled data to fit those parameters, but then also for the unlabeled data, we go through an iterative loop. On each E step, we estimate the labels for every noun phrase and noun phrase pair that we have, which is 20 million noun phrases, and that number is squared for noun phrase pairs. In EM, we would just use our current black functions on this current iteration to estimate the probability distribution over the labels for each of those 20 million noun phrases and 10 to the 14th noun phrase pairs. And then on the M step, we would just use all those probabilistic labels to retrain each of those black arrow functions. And EM would lead to a locally maximum likelihood solution, and that would be a way to do it if we had a lot of computation time and machines, but it doesn't really work for the size of the data set that we have. For example, there are really our 10 to the 14th noun phrase pairs, so it's not practical to calculate on each iteration that many labels. But essentially, that's what you'd like to do if you had infinite computation, because it would be a way of at least getting a locally maximum likelihood solution for the parameter fitting the data. So what NELL does is what I'll call E prime M prime. And E prime is just like the E step. On every iteration, NELL looks at the noun phrases and it assigns labels, but not to every one and not to every pair of noun phrases, just to the ones in which it's most confident. So instead of labeling all 10 to the 14th noun phrase pairs, it just labels the 250 for each function in which it's most confident. And then on the next iteration, it might pick up another 250. And it does that for each of its functions that it's learning. Okay, and then the M prime step, again, is on every M prime step, it then uses those things that it's decided to label, along with their confidences, to retrain the different black functions that it's training. Only it doesn't, for example, if you think of the context-based function, there are actually 50 million contexts, the 50 million most frequent contexts around noun phrases that NELL considers. And it doesn't actually consider all those features on the M step. It just considers the contexts that have the most information content for making the prediction. And it uses heuristics to make these choices. So you can think of it as related to EM, except that there's over the iterations, there's a growing number of noun phrases and noun phrase pairs to which it's actually assigning labels. And also on the iterations, there's a growing set of contexts out of those 50 million contexts that it's also considering as the basis for making the predictions. Okay, so there's the algorithm. And so that leads to an architecture that's very simple and very commonsensical. It's this. There are these different types of learners. As I mentioned, one type of learner looks at the context around noun phrases or the context between two noun phrases in the case of relations. One of them looks at HTML structure at particular URLs and learns wrappers. Another one looks at the morphological features, the character string inside the noun phrase. And NELL's got a knowledge base, the one we were browsing. You can think that knowledge base is essentially, that is the set of latent variables being labeled during the E step. That is the subset of possible beliefs that it has decided to commit to, the growing set over iterations of possible beliefs that it's decided to commit to in the E prime step. So in the E prime step, every one of these learners gets to make predictions of new beliefs to add to the knowledge base. They get looked at by the evidence integrator, which decides on a final confidence to assign to each of those proposed beliefs. And then on the M step, each of these modules gets to look at the knowledge base, essentially the E prime step labeled beliefs and their confidences. And on the M step, each of these gets to retrain themselves using the current knowledge base. So it's just a simple iteration, simple iterative loop that's run about 160 iterations since January of re-estimating what set of beliefs we should believe given the web, and then retraining all these classifiers accordingly. All right, so it's a very simple strategy. I won't go into the details of each of those learning algorithms because it would take way too long, but I will just show you some examples of what's actually learned. We saw a lot of evidence for these kind of context patterns when we were browsing the knowledge base. But here, for example, are a sample of the context patterns that are learned for the relation athlete plays sport, right? So you see like ARG1 was playing ARG2, or ARG2 megastar ARG1, so forth. My favorite still is ARG1 is the Tiger Woods of ARG2. So the second module, the one that learns the morphological structure, that's actually a logistic regression function, a logistic function that's trained using logistic regression, has many, 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 many features that it considers. And I hope you can read this, but I'll read it to you. What this table is showing us is for a couple of the different categories, like these first three, the category mountain, that's one of the categories that NELL is trying to learn to classify into. For mountain, the three of the most salient features are if the last word in the noun phrase is P-E-A-K, as in Pikes Peak, then there's a high positive weight that that's a mountain. The second line here says if the last word is mountain, that's a high positive weight. The third line says if the first word of the noun phrase is mountain, that's a large negative weight, meaning it's probably not a mountain. That would be like mountain bike is not a mountain. It's a noun phrase that begins with mountain. And so forth. Music artist, you can see if the part of speech sequence is a determiner followed by plural noun phrase, like the Beatles, then that's a good morphology for being a musical artist or a musical band. For newspaper, it's things like, does it end in sun, and so forth. And one of the pleasant surprises in doing this work is when we started this, we thought this kind of morphological analysis would be useful for a few categories, like names, like a lot of names. Like if I say to you, Obelinsky, it's probably not a word you've heard, but you probably think, oh, probably a person, because it ends with ski, right, as do a lot of Polish names. So we thought when we started this, it would be good for a few categories, but we've been very pleasantly surprised at the diversity of categories for which morphological analysis actually gives remarkably good results. And then the third module, the one that learns URL-specific classifiers, Here's an example, and this is based on the work of William Cohen and Richard Wang, who developed a system they call SEAL that is this module. But essentially, for example, learn for the relation book author. If you go to http://lifebehindthecurve.com, that particular web page, then if you find this particular pattern, which is some list of phrases of the form X by Y, then the X and the Y will satisfy, according to this rule, the book author relation. So these are these very typically HTML structure patterns. And so if you think about it, what's interesting about these three different types of learned extractors is they use three independent sets of data. And the good thing about that is it means they make independent errors. And the good thing about independent errors is if you're trying to get the error rate of the conjunction, it's the product of the errors. So if you have three systems, each of which makes a 20% error, but you have three of them and they're independent, the error of the combined system is 20% times 20% times 20%, which is a good error rate. You can do the arithmetic. So part of the name of the game in NELL is to make up these different learning things that extract information based on different kinds of evidence, taking advantage of the large scale and redundancy of the web. And by virtue of making those have independent errors, they can actually train each other very well. So if, well, I'll just leave it at that. All right, and so the coupled training that using this, I'll call it the E prime M prime algorithm, really does help. Here in an earlier version of the system that only ran a few iterations on a smaller set of data, here's what happens on average in terms of precision if you train on those 10 to 20 labeled examples that we have, plus unlabeled data, but you do it in an uncoupled way. The first way we talked about and rejected as unfair or unwise. Here's the accuracy you get if you only use the HTML features instead of only using the context, the language context. And here are the accuracy, the precisions that you get if you do coupled training the way NELL does. And you see there's a significant effect. In fact, if you look at the individual predicates, here's a sample of the predicates with the accuracies for those three approaches. What you see is that when you couple them, for a large number of the predicates, you get remarkably high precisions. And in fact, the other thing you notice here is something that we continue to see in the system, which is that if you ask me how accurate the system is, or how precise the system is, the answer is it's almost bimodal. So there are a number of predicates where the precision is very high, in the high 90s. And then there are a smaller number, but a noticeable number, of things like sports equipment, where the precision is 23%. And so when we continue to see this, that the majority of the predicates that are in the ontology, NELL is learning just fine, but then there are a smaller number, but significant number, where it's tanking. And I don't have a good explanation for that. We have fallen, though, into the mode of whenever we see one of those troublemaking predicates, looking at it and thinking about, maybe we should add another predicate that's going to be mutually exclusive with it and nearby, so that that predicate can't kind of go crazy the way our city one did that we were talking about, right? Like for that example where it was getting denial and other traits, we might respond by adding a new category to the ontology called human traits, and then pointing out that that's exclusive with cities, and often that'll repair the problem. Okay, so I told you there were two good ideas, or two ideas that I'm proud of about NELL. One was this idea that coupled training really is a good idea if you've primarily got to rely on unlabeled data, because those coupling constraints turn each unlabeled example into a constraint on the joint choice of parameters for all those functions. Okay, so if that's a good idea, it raises this obvious question: where can we get more coupling constraints? Well, we could try to think of a fourth type. We went through 3 types of coupling constraints. But another thing we could do is we could try to learn them, or get NELL to learn them. And this, again, is in the spirit of, let's build a never-ending learning system that once it gets good at one thing, it can now be in a position to learn something else that helps it learn something else, and so forth. So why don't we get it to discover new coupling constraints? I know there's work similar to this here in Oren's group as well, but we wrote a kind of standard first-order horn clause learner, and NELL, and we added a 4th module to NELL, which is this rule learner, and on every iteration, this rule learner retrains itself and tries to learn rules, but they're not rules about how to read. Their rules that it tries to learn are about empirical regularities in the world that it's reading about. So for example, this rule that it learned says that you should predict that athlete X plays sport Y if athlete X plays for team Z and team Z plays sport Y. Now you and I know that's kind of common sense rule, but NELL didn't know that in January. It knows it now, at least with conditional probability 0.93. And what's nice about this is these rules allow NELL to infer beliefs that it maybe can't even read, as long as they follow empirical regularities that it's been able to establish from the hundreds of thousands of things that it has read. Let me just show you some good and bad rules that it's learned, just to give you an idea. So here are some of the rules that it has learned. Like this one here says, athlete X plays in League Y if they play for team Z that plays in League Y, or the city X is in state Y if it's the capital of the state Y, and furthermore, the city is in USA. Actually, this is interesting. You and I know that logically we don't need the second precondition, but NELL adds it because it gives it a more accurate rule. And I think that's because it reads more accurately US cities than it reads foreign cities. And one way it can get evidence that this rule, one way it gets negative examples of the rule is it sees it make predictions and it believes them to be false from what it has read. And if you imagine that it's more accurate in reading about US cities than it is non-US cities, then you can imagine that adding this precondition actually does improve the empirically determined conditional probability accuracy for the rule. So in some of these rules, we do see it adding these clauses, and you go back and you look at the evidence it was using, and you say, yeah, it really does improve the accuracy. And so the rules can kind of patch over or compensate for poor reading in a funny way. It also learns bad rules. Here's one at the top there that says, Team X plays in the NBA if Team X plays basketball. Now that's false. I'm sure UW has a basketball team. It doesn't play in the NBA. But if you look at the evidence, and it believes this with remarkably high confidence, that's a map estimate derived from its evidence, which was, it had 35 examples, positive examples, where this rule applied and made a prediction which NELL had already read to be true. It had 0 negative examples, 0 examples where this applied and it made a prediction which NELL had read to not be true. So at that point, it hadn't actually read very well about college basketball. In fact, NELL typically reads best the things that are most frequently stated on the web. And professional teams get discussed more. And so at this point, it hadn't really read about the NCAA and which teams play in the NCAA and stuff like that. And then it had 35 other unlabeled examples, just examples where the rule applied and it hadn't read yet one way or the other. So some of these rules, like this rule, is obviously wrong, we know, but it couldn't have known because as far as its evidence went, there was plenty of positive evidence, no negative evidence. But the error was a consequence of the skewed sample of the world that it's able to read. And so that's kind of an unfortunate interaction that we're still trying to figure out how to deal with. So to finish off this, the point is, if you think about those kind of rules, they're really more coupling constraints. Like that blue rule is this new coupling constraint between the three relations that it mentions, play sport, plays for team, and team plays sport, that didn't exist in our initial coupled network of functions that was the source for good idea one. So in this very literal sense, NELL is now learning these horn clause rules, which are additional coupling constraints that allow it to thereafter learn even more accurately the extractors that led to it being able to learn the rules. So there's a nice synergy there. But I just tell you where NELL is today. So here's a plot that kind of summarizes very quickly how NELL is done since January. The vertical axis here is the number of beliefs in its knowledge base. You'll see it grew very nicely at the beginning. The red numbers are the estimated precision of that knowledge base over time. Unfortunately, you see those numbers going down over time. And that explains why in June, we decided it was time for humans to get into this loop that had been running for 5 months. And so we decided we would begin, and we have ever since, a process where after every 10 iterations, one of us will look through the knowledge base and spend 5 minutes per predicate on average, scanning the beliefs, and if things look like they've gone horribly awry, we just draw a line and say, please forget everything you learned after this point for emotions, because these all aren't, well, it's some weird mix of emotions and non-emotions, so forget all that. And then we'll label maybe on the order of a dozen negative examples right around that point. That takes you about 5 minutes. It's something you can realistically do. It's not the best way to have human interaction with NELL, but we had to do something. And that's what we've been doing about every 2 weeks since, and that explains the little chunky form of the curve after there. Unfortunately, what you see here is that on average, at least for the first 6 months, it was not happening. But if you actually drill down and look what was happening, for the majority of those predicates, like actually 75% in that first group, it was doing just fine. But 25% of the predicates were doing poorly, and they were going crazy. They were like sucking up all the noun phrases and saying, oh, here's a cookie, here's a baked good, here's another baked good, here's another baked good. In fact, baked goods was one of the categories that did that because of the internet cookie problem. All right, so I want to wind up just by telling you some things that are not in the version of the system that's running openly on the web with the knowledge base being updated, but which are recent research developments that we hope to get into the system soon. And also as a way of saying what are some of the shortcomings of the current system. So the first one is, as I'm sure many people, especially here where open information extraction is very popular, have noticed, NELL has a fixed ontology. And even though it's very useful for NELL to have an ontology, it's not useful for it to be fixed. And so one of the things we're interested in is, can we add a module that will suggest new relations and new predicates? One is some work that's being done by Tahir Mohammed and Stefan Hrushka, which is actually similar to some playing around that Oren and Steve and I did with using TextRunner in a similar experiment. But the idea is this. Let's just consider the categories that are already in the ontology, and let's ask the question, can we discover the most frequently stated kind of relations among these two categories? So for example, let's consider a category like musician and musical instrument. And to find frequently stated relations between those, what we can do is we can take the known musicians that NELL has already extracted, the known instruments that NELL has already extracted, look for sentences in which a musician and a known instrument occur, and then if we can find the same pairs occurring multiple times, let's look at the distribution of context between them, and let's co-cluster the noun phrase pairs that are known music instrument and musician pairs and the context that co-occur with them. And if you do that, you actually get quite reasonable relations. So in the case of musical instrument and musician, you find one of the clusters has these four contexts as the main context, like arg1 master, arg2, or arg1 virtuoso, arg2. And the pairs of noun phrases that match them are things like sitar, George Harrison. Or between disease and disease, we get something which you might call is due to. Pinched nerve is due to a herniated disc. Or between cell type and chemical, this clustering discovered epithelial cells that release surfactant and neurons that release serotonin. And between mammals and plant, we get this. So a lot of these turn out to actually be quite reasonable. And one reason that we've expanded the ontology a lot in the last few months is we started looking at these things and saying, well, we really should just add it. So we're manually adding these things. And I think soon we'll try to make this into a module in the system. There's another sense in which NELL is actually already, in a way, extending the ontology. And that's because people say the darndest things. And NELL can read on the web things like livestock is a subcategory of animals, and chickens are a kind of livestock, even though it didn't start with the notion of livestock. So, for example, as it points out here, one of the leaf nodes in the ontology initially was chemicals. And NELL started reading chemicals. It got carbon dioxide, ammonia, and gas. You and I look at that and we say, well, gas isn't really a chemical. It's a category of chemicals. But NELL couldn't distinguish that. But then Burr Settles, our postdoc, said, well, I'm going to add the relation type has member to NELL, and I'll give it a dozen training examples of that, and then it'll learn to read type has member. In fact, he added it to make it easier for NELL. He added versions of that for each of the ontology categories. So it's animal type has animal, and chemical type has chemical. That way we get better learning because we can better type the relations. It's a way of essentially coding that two things, if they're going to be subcategories, should be both members of the supercategory. But anyway, when you have NELL, then just the current version of the system, just when you introduce these relations like chemical has subtype chemical, then you find that gases has subtype ammonia, carbon dioxide, carbon monoxide, methane, sulfur. It just falls out, it gets red. And similarly, animal has livestock, animal has predators, animal has large animals and small animals. These are all now in the system, not because we changed the modules, but just because we added to the ontology this relation. And so for example, for animal has subtype animal, here are the kinds of patterns that it learned that it's using to extract the fact that livestock, I guess this would be chickens, like whatever it is. You get the idea. Okay, so what I think would be interesting in the future is to put together these two ideas and build an ontology extender that both does the kind of statistical clustering that I talked about first and tries to corroborate by reading that this is a new ontology extension that people care enough to talk about on the web, as opposed to some arbitrary unnamed subset of the category animals. And that way we can kind of use popularity and discussion on the web along with statistical analysis to jointly constrain the extension of the ontology. Okay, so very briefly, I want to tell you about this one because I want you to all come play this wonderful game that's going to appear on the web within the coming month called Polarity. Remember that name, type it in frequently so you're the first to know when it comes up. Burr Settles and Edith Law and Louis Van Ahn have been developing a game that we hope a lot of people will find entertaining. It's a kind of word trivia game that if people play it, then it's going to be also giving labels to NELL on an ongoing basis. And so this will be a way of trying to tap into crowdsourcing kinds of things. And I'm especially interested in this because it isn't that much fun to spend 5 minutes per predicate going through these things by hand. Okay, so I'll stop there. And if you take home any message from this talk, I think the main messages are these. Number one, think about how wide open the research problem of never-ending learning really is. Nobody knows how to do this. It's 2010. There are plenty of pieces around. It's time to do more of this kind of work, I think. And you can make such an important contribution in 2010 because nobody's working on this problem. It's really a rich problem. There are a lot of great PhD theses in this. So think about things like, why don't I take that robot that I'm working on and turn it into a never-ending learning robot? Or why don't I take that game-playing thing that I'm working on and build a never-ending chess learner? Why don't we have a never-ending chess learner? Or why don't I take that vision problem I'm working on and build a never-ending learning street lamp with a camera on it that just learns what the heck is going on in that intersection and gets increasingly sophisticated about whether it should call the police or not, or if you care about privacy issues, forget that. Just whether it should tell the light to turn green or red on increasingly sophisticated information. So, you know, there are a lot of things that in 2010 we could do that those guys back in 1950 couldn't. And so we shouldn't fall into the trap of taking their old formulations of computer science research. We should make up 21st century research problems. So that's probably the main point of this talk. Thank you.